Good day, dear professors, teachers, and students. Welcome to the third video narrating the story of the third form in the evolution of the binomial theorem. Aryabhata and Bhaskara II extended the root extraction techniques beyond quadratic and cubic equations, developing methods applicable to fourth degree and higher roots. They achieved this by applying algorithms to cube roots and constructing numerical root tables. The discovery of this Indian nth root approximation emerged through intuitive uses of the binomial type expansions centuries before their formal symbolic expression. The Indian studies in number theory and root approximation were later strengthened and generalized by Islamic mathematicians. During the Islamic Golden Age, Al-Karaji introduced the concept of binomial coefficients through symbolic calculation. The nth root approximation formula. What is the formula of the nth root approximation and how do we use it? There are two forms or formulae to take note of. For the correction or decimal part, we compute for b. And the formula is b is equal to a minus a raised to n all over n a raised to n minus 1. Alright, and then to complete the nth root approximation, we use the formula here in number 3. The nth root of a is approximately equal to a plus b. But first, to find the nth root of a, we choose an integer a such that a raised to n is less than or equal to a, and a plus 1 raised to the power of n is greater than a. This method is based on the truncated binomial expansion and reflects early numerical approaches developed in India and later formalized by mathematicians like Al-Karaji in the Islamic Golden Age. Alright, so let's consider an example. We want to find the fifth root of 350,000. So we set a is equal to 350,000. So first step, we're going to break down the root into two parts, a and b. So we have fifth root of a is approximately equal to a plus b, where b is very much smaller than a. So a is the integer or the whole number part of the root, and b is a much smaller correction term, often representing the decimal part. Alright, so the next step is to look at the numerical table of numbers when raised to the fifth power. We find that we can take a is equal to 12, since 12 to the fifth is equal to 248,832. And 12 to the fourth is 20,736. We cannot take a equal to 13 because 13 to the fifth is 371,293, and that is greater than 350,000. Now, to estimate the decimal part, we consider the formula for the first order correction b. So b is approximately equal to a minus a raised to the n all over n times a to the lower degree n minus 1. So we will compute b in the next step. So computing for b. Now, take note that the first order correction b has a dimension that resembles the Newton-Raphson method. Here we can view f of x is equal to x raised to the n or an. And then the first derivative of an is n times a raised to the lower degree n minus 1, right? So we have the function of a here, and we have the first derivative of the function of a. And then in this formula, a is considered as being slightly smaller in comparison to a times n times a raised to the power of n minus 1. Okay, because we need to multiply a with this denominator here. Try to figure it out. Use Newton-Raphson's method. Now substituting the values. So we obtain B is approximately equal to 350,000 minus 248,832 all over 5 times 20,736. So our B is approximately equal to 0.97577. Thus, the correction term B refines our initial estimate of A is equal to 12 because we have the decimal part. Alright, so we now add A plus B to obtain a good approximation of the fifth root of 350,000. So A plus B is equal to 12 plus B, 0.97577. So the root is 12.97577. So take note, this is a first order approximation. Higher order terms improve accuracy. Now let's calculate the fifth root of 350,000 using GeoGebra Classic. Alright, so we type 350,000 raised to 1/5. Okay, and then let's have 5 decimal places. Alright, so the fifth root of 350,000 is approximately equal to 12.84735. So our approximation of 12.97577 is slightly off. Okay, because the fifth root of 350,000 is approximately equal to 12.84735. So note, this difference arises because we're only considering the second term of the binomial theorem expansion, expressed here through derivatives. Later, when we study the European narrative of the binomial series, we will learn how to refine this method for better approximations. Alright, so to experience and appreciate the third form, the Indian nth root approximation, please answer 2 out of 5 of these items here. So, thank you so much for watching.